Hello ladies and gentlemen, today we're going to learn about electric fields and Coulomb's law. Let's get to it. Okay, in order to start off and to understand what a E field is like, it's easy to describe it like the gravitational field caused by the Earth. Okay, we know that as we drop something, that something will go towards the Earth because of this gravitational field that surrounds the Earth. Now, an electric field is kind of the same, except it deals with charges and it also deals with things that can also attract as well as repel. Now, the E field is the area around a charge. As you can see in the presentation, we have a positive blue charge and we have a negative red charge. Notice how the positive blue has E field lines coming out of it and the red one has E field lines going towards it. Okay, and that's going to actually help us explain why like charges repel and unlike charges attract. All right. Now, you might have seen or experienced a E field when we were playing with the Graaff Generator in class, and you can think of the E field like when that generator is running and you put your hand kind of near it but not close enough to get shocked, you kind of feel like this force field on your hands. That's what we call the E field. And we feel that because there's tons of negative charges that build up around that generator. All right. Now, the equation for the E field is the E field is equal to the force generated by the field divided by the amount of charge. You actually don't need to know this equation, but for your notes, here it is. This here is a drawing of what two charges look like next to each other. Here we have a negative charge and a positive charge. Notice how the negative charge has arrows going into it, and the positive charge has arrows coming out of it. Right? Now this shows something that is attracted. And we can say that it's being attracted because the lines actually interconnect compared to something that is like charges, they repel. So you can see here that all of the arrows are coming out of the positive charges and they don't interact, they don't connect. Okay, so if we have two like charges, they will repel each other and you can actually feel that repulsive force. Right, now here's the rules for drawing E field lines. E field lines are lines that indicate the strength and direction of the field. Okay, and then we do that with the arrows and of how close the arrows are to each other. Important, very important rule. Just like in Ghostbusters, all right, the lines cannot cross. Whatever you do not cross the lines. Draw them closer together to show strong E field strength, but never had the E field lines actually crossing. All right. Now, with the concept of E fields, we have something very cool called shielding. Now, if there are some of you out there that are preparing for the end of the world, Mr. Lee is here to help you out. Okay, so what's the most important thing that you have electronically? Your cell phone, of course, and at the end of the world, right, there's going to be nukes everywhere, or oh my gosh, let's not think about that. But if there are stuff like that exploding all around us, we have these things called EMPs, or electromagnetic pulses, just shooting everywhere, like pew, pew, pew. You can't really see it. It's just a magnetic thing that shoots out across the sky. And you might have heard about it in sci-fi movies, but the cool thing is that these EMPs will make anything that runs on circuits useless unless you shield it. Okay, and this is how you shield it. Step 1, get your electronic device. Step 2, get a metal trash can. Step 3, put the electronic device inside of the metal trash can, and then step 4 is save yourself because you can't use it if you're gone. All right. Now, if you do that, your electronic device will be saved because of this rule right here. The E field is 0 inside a charged conductor. So what does that mean? So if we were to get a metal cage, okay, and we get electricity, and we course the electricity through the metal cage, and you go near it, and zzz, 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 you get shocked. Ow, ow, right? Ah, it hurts, it hurts. Surprisingly enough, all around the metal cage, you can feel that E field. However, on the inside, you feel nothing, no E field at all. That's what we call shielding. Okay. Now, using that same idea, let's ask this question. Where are you safe during a thunderstorm? In a car or outdoors? Alright, now common sense, or hopefully what your parents and other people have taught you, is that you are the safest inside your car. And it's not because your cars have rubber tires. Okay, now think about it. If there's a thunderstorm and lightning storm, lightning shooting everywhere. You have lightning striking from the heavens high up there in the clouds, and it's coming down that great distance, and it hits your car. Do you think that the lightning will care about like a 1.5 foot tall wheel that's made of rubber? I don't think so. It's not gonna care. It's gonna hit your car regardless. And so when it does hit your car, you're actually shielded because of lightning. Lightning wants to go wherever there's a conductor, okay? And the outside of the car is made of metal, usually, and the metal will conduct the electricity away from you. And inside of the car, you are safe, as long as you're not touching anything metallic, because inside the car there's no E fields being generated. Yeah, and in fact it's really cool, but once it reaches the tires, it hops over the tires and it goes into the ground. So be inside of your car because the metal frame actually saves your life. Okay? This shielding idea also explains why you can't get reception inside of a tunnel or a steel bridge, because you're being shielded for any electromagnetic wave. Whoa, funky word. Right? Pop quiz. Alright, which of the field is stronger, A or B? If you said C, you're not paying attention. But the answer is B. Ding, 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 ding. And we know that because of the density of the lines. There's a lot more lines there. Okay, Coulomb's law. Woo, we're finally there. A couple of things about Coulomb's law. You need to know this E. This is the elementary charge. 1.6 times 10 to the negative 19 coulombs. This is the value we give to every charge, whether it's positive or negative. If it's a positive charge, we say it's positive 1.6. If it's negative, we say it's negative 1.6 times 10 to the negative 19. Now, if it's, well, this explains why if you have one positive charge and one negative charge, we have a neutral, because positive 1.6 plus negative 1.6 equals 0, right? Okay. Now, with Coulomb's law, we need to know the type of forces. If you have two like charges, that's going to be a repulsive force. If you have two unlike charges, that's going to be a attractive force. Okay, and we know that. Okay. Now this next simulation is going to show us the properties of Coulomb's law. Alright, so here we have Coulomb's law. We have two like charges that is separated by a distance. Right here, we can see the force magnitude, right? Now, if I drag this charge close to the other one, look what happens to the force. It increases. Now, important thing to note, it doesn't tell you if it's force 1 or force 2 because of Newton's third law. Whatever Q2 is doing to Q1, Q1 is doing to Q2. So Q2 is pushing Q1 away, and Q1 is pushing Q2 away with the same amount of force. Right? Alright, so what would happen if we made one negative? Look at the arrows, boink! Look at that. Okay, you notice that they are now an attractive force. And the force between them increases as you bring them closer together. Very nice. So a couple of things we need to know about Coulomb's law. You need two charges, minimum of two charges that are separated by a distance. And we can write that in a formula like that. That K is what we call Coulomb's constant. I'm going to explain that to you in a bit. Very important to understand the relationship force has with the distance away. Okay? As the distance, the two charges are away from each other, increases, the force decreases. It gets weaker. And we call that the inverse square law. And I'll show you a graph that explains that in a little bit. Okay? K is Coulomb's constant, and it's 9.0 times 10 to the 9. A lot of nines. Newton meter squared divided by c squared. You don't have to memorize that. The formula sheet gives it to you. Q1 is whatever the charge is for one charge. And Q2 is whatever the charge is for the second charge. And R is the distance between the two. Right? Simple enough. And this looks a lot like the universal law of gravitation, except the universal law of gravitation, instead of a K, we had a capital G. And instead of Q's, we had M's for masses. Right. With that reference, you need to know that the electrical force is much stronger than the gravitational force. That's why when you rub a balloon on your hair and you can stick it on the wall, it doesn't fall, because gravity is actually a really weak force compared to the electrical force. Okay, now I'm going to go straight into the difficult stuff. I'll give you a practice problem, but with 3 charges. Oh, before we get into that, here's a graph explaining the inverse square law. As the radius increases, the force decreases exponentially. As the radius between the 2 charges decreases, as the things get closer and closer together, the force between them increases. Alright, so here we have 3 objects that are placed as shown, bloop, bloop, and blop. Find the net force on the object with a charge of -4 microcoulombs. Micro is just a fancy way of saying 10 to the -6. They're separated by 20 centimeters and 20 centimeters each. Okay, this is what you're going to do. Don't freak out. It's actually relatively simple. You are going to find the distance that separates this charge from this charge, because that's what R is. Right? And Pythagorean theorem does that. Secondly, you're going to find out the direction of force. So this positive 5 microcoulombs is pulling this -4 to the left. That's F1. F2, this -5 is pushing this -4 because, remember, like charges repel away to the bottom and right. That's F2. All right, once you have that established, where do we go next? Coulomb's law. Let's find F1. All right, K is 9 times 10 to the 9. Q1 is 5 microcoulombs right here, and this is going to be -4. And you might be asking yourself, Mr. Lee, where'd the negative go? Well, the negative doesn't matter when you put it in here, because all you need to know is the direction of the pull or the push. Okay, divided by the distance in between, which is 0.2, and that gives us a magnitude of 4.5 newtons to the left. And that's where the negative comes from. That's where the left is. Okay? So you have one of the forces. Now let's find F2. Same steps. All right, 5 right there, 4 right there, and we find that F2 is 2.30 newtons. Try it on your calculator, see if you get the same values. All right, now here we have 2 forces. One's going to the left, one's going bottom right. What do we do? If you say vectors, good job. You've been paying attention all year. Okay, let's do it. F1 doesn't have a y vector, it only has an x, so that's going to be easy life for us. F2, however, has 2 kinds of vectors, x and y. So we got to break it up into its components, x and y components. All right. If we find the x component, we get 1.6, and we got that because F2 is 2.3, and cosine of 45 times together is 1.6. And we use sine for the other one, so it'll be -1.6 or 1.6 going down. Okay. And I'm going to write this in coordinate form, so that makes the addition a little bit easier for us. So -4.5, that's F1 going to the left, and we have positive 1.6 going to the right, plus 0. F1 is 0 for the y, this is not going up or down, plus -1.6. And we get that as our coordinates for the net force, which just means we have 2 sides of a triangle. If we have 2 sides of a triangle, you guessed it, Pythagorean theorem. If you do that, we get 3.31. But we're not finished yet. Nope, we need to find the direction, and that's where we find theta. Okay, we do that with trigonometry. So our final answer gives us 3.31 newtons at 209 degrees, or 29 degrees bottom left.